Hello. In this video, we will cover numerical approximations using Euler's method. So, as we've discussed previously, a general first-order differential equation looks like the following. We have dy dt equal to some t and y stuff, and then we have an initial condition. In previous videos, we've gone through and we've solved first-order differential equations using a variety of different methods. However, in general, those methods do not work. Those are for specific, rare cases, and in general, symbolic techniques do not work. So you may not be familiar with this symbolic manipulation term. That just means where we go through and the method that we use for solving a linear first-order differential equation, where we just use a bunch of symbols and move things around, and by moving things around, we're able to go through and solve the differential equations. The exact equation method is a symbolic manipulation method. It's simply just moving symbols around, and you're able to go through and come up with a solution. In general, differential equations cannot be solved using symbolic manipulation. So because of that, what else can we do, right? So how can we go through and be certain that we can go through and solve a first-order differential equation? Well, so the answer to what we can do to go through and solve a differential equation when we can't use symbolic manipulation is to recall direction fields. Right? So what do we have with a direction field? Right? We have we have plotting of slopes, right? We have a picture that contains a bunch of slopes. Right? And what do we know? We know that any solution to the differential equation has to actually fit up against those slopes, right? So the slope at each point is the slope of the tangent line that you'd get for the curve that went through that point. Okay, so you can't have the curve go through that point and not be tangent to that slope, right? So the direction field does enable us to go through and gain some insight into what the solutions would look like because of the fact that any solutions that are that you fit onto that direction field have to fit onto those slopes. All right, so what we want to do next is to actually explore how we can use that fact to go through and try and come up with a solution to the differential equation using a numerical technique, right? So we're going to use a numerical technique. All right, so let's take a look at a direction field. So here we have a direction field. As you can see, it was created using Geogebra. And what we'd like to do is be able to go through and see if we can use this to come up with solutions to differential equations. And let me be clear about what I mean by a solution, right? If you can't go through and solve the differential equation using the symbolic technique, you can't go through and come up with a function, then what we're going to be looking to do is to come up with a solution that's just going to be a bunch of points, essentially, where what you can do is you can figure out by looking through all of the points what the output would be for a given input, but you wouldn't actually plug it in the traditional sense. Instead, we would generate a list of input-output pairs, and then we'd be able to use that to identify solutions. So it's a different idea behind a solution, right? So what we've talked about up to this point is that solutions would actually be functions. Here, we're going to have a solution as input-output pairs. So that will become clear when we actually go through and solve one. All right, anyway, so if we wanted to go through and use this to try and find solutions, how could we do that? What we'd want to do is can we go through and draw curves that fit onto these slopes? If you can draw a curve that fits onto the slopes, then you've got a solution. I mean, that's all there is to it. All right, so let's go ahead and try that. What would that look like? What would that involve? Let's zoom in. See the slopes a little clearer. Let's say we were starting at 0, 0. Let's say we were starting here. So that's our initial condition, is that t is 0. So this is the t-axis here. Y is 0. This is the y-axis here. So we're starting at that point. And what we want to do is we want to go through and draw a curve that, that is tangent to that. Okay. And then what we're going to do is it'll be tangent. We want to draw a curve that's tangent to that. And then as we move along from left to right, it's going to have to change. The curve's going to have to change to adjust for the next set of slopes. And I'll show you how you can do that. All right. So you can see how the line right there, see how it's a horizontal line. So the slope is 0 there. Right. So what we can do is we can say, all right, we're starting there, and we want to draw a line that has a 0 slope. So what would that look like, right? So if you just kind of start there, draw a line, it would look about like that, right? And what you can do is you can go through and you can draw as far as you want. But in this case, since we're going to go through, we've got these increments, what we're going to do is we're going to draw it until we hit the next increment. Let me try it again because it got all messed up when I hit. Anyway, that's the best I can do to draw flat lines. It's not quite flat, but it's close enough. And then you can see at that point we get to the next slope, and so the curve has to fit onto that slope. And so what we can do is we can go through and just use that slope to kind of tell us, what the slope should be to get to the next point. And one of the things you can see, I'm not technically drawing a curve here. I'm going through and I'm drawing pieces, but if you smooth this out, you'd get a curve. And then the next one, we can go through and you can see here's the slope at this point, and then it's a little bit steeper here. So somewhere between those two is the slope that we would have here. So maybe it looks about like that. Okay, and then we get to our next increment. And then we could go through and do the same thing because it's between these two. So this one's a little bit steeper than that one, and so we'll get a point that maybe looks about a line that looks about like that. Okay, and so you can see that I've gone through and I've been able to draw a curve, right? It's not completely smooth, it's little line segments, but it does fit onto the direction field, right? And so this, if you just smoothed it out, would actually give us all the points that if you plugged them into the direction field, would solve the direction field. I mean, or sorry, if you plug them into the differential equation, would actually work for the differential equation. And so what we've been able to do is we've been able to go through and solve the differential equation without actually going through and doing the symbolic manipulation using this numerical technique. Okay, and if you want to, and just a couple of comments here, if you want a smoother curve, what you can do is you can just take the slopes and move them closer together. And so don't go as far before you kind of recalculate. And if you make the increments small enough, then it will become as smooth as you want it to be, right? To just show you another example, like we could pick a different starting point. Like let's say we were starting here. So this looks like the point 0, 1/2, right? So we've got t is 0. This is the t-axis, so t is 0, and then it looks like y is 1/2 here. And so if you start there, we've got, you can see there's the slope. So it's saying, you know, we want to draw something that fits onto that. So if we use the line segment here, we're guaranteed to have, you know, at this point, we know that the slope will be, you know, given by this whole line segment. And then when you get to this piece here, you recalculate and then recalculate, and it goes up off of the picture. And so you could see there's one solution, there's another. You could start here at 1. We would get go to there, and then we'd go up off the page. And you could zoom out maybe to draw to, you know, kind of see what this is looking like, right? But you could see that we can go through and we can draw these curves, quote unquote, right? So they're not completely smooth unless you go through and make the increments really tiny. We can go through and we can draw these curves that fit onto the slopes. And since the curves that fit onto the slopes solve the differential equation, the curves that we're drawing solve the differential equation. Okay. So again, this is a numerical technique because we're well, you'll see in a second, but the way that you go through and do the process here is by just doing number crunching. Like we're not manipulating symbols in any way, shape, or form. And so we found a way around actually going through and solving the differential equation symbolically. Okay, so that's the basic idea is, you know, behind Euler's method is to draw these, you know, to go through and fit a line onto, actually, maybe I should comment on that. One way to look at what we just did is you fit a line, you start here, you fit a line onto that slope until you get here, and then you fit a line onto that slope till you get here, and then you fit a line onto that slope, and then a line onto that slope. That ensures that the curve you end up with will fit onto the slopes at the appropriate points. Okay, and it all involves just using a slope, right? You have a starting point here, that's the slope there, and then a line segment, and then a slope there, and then a new line segment, and then a slope, and then a new line segment. And so that's going to be the method that we're going to go through and formalize next is that basic idea. All right, so I want to be clear that that's understood. So to go over the same idea for this curve here, quote unquote curve, we start off here. You've got a little slope there. We fit a line segment onto it, step out. You get to this slope here, then we recalculate there. So we've got a slope there. You fit a line segment onto it, jump out to the next spot where we have a slope, recalculate. You've got a new line segment, and that's the basic idea. Okay. So let's go through and formalize this, write up what we actually, what we're actually doing here, write it up into a formula, and then we can actually try it on a differential equation and see how well it works. Okay, so what do we start with? That's an important place to begin is, what does our differential equation start with? And we started with that. Started with that on the previous page, and that is that given dy dt equals f of t comma y, and we have y of t naught equals y naught. Right, so that's the way that's our basic first order differential equation. So that's our starting point. All right, so this starting this initial condition here where we have y of t naught equals y naught, if we go through and rewrite that into a point notation format, this could be translated into t naught comma y naught, right, is our initial condition. So that's how we're going to start. So we're going to start with t naught comma y naught. All right, so if you recall from the discussion that we just had, the first thing that you want to do to go through and construct, your curve, quote unquote, is that you want to find the slope at the initial condition, and then we're going to use that to define a line segment. So we want to start off by finding the slope. So we're going to find f of t naught comma y naught. Now that's going to be the slope at that's going to be the slope at t naught y naught. Why is it the slope? It's because f of ty equals dy dt. dy dt is the slope of y, right? And y is the solution to the differential equation. Did you catch that, right? So dy dt equals f of ty. dy dt is the derivative, right? It's in the normal derivative format. It's the derivative of the function y, and the function y is the solution to the differential equation. So it's the slope of the solution to the differential equation, y. And so we can go through to find the slope by just taking points and plugging them into this f of ty, and that's what we've done. So we start off with the point t naught y naught. We find the slope there. So this is the slope. Next, we go through and we want to use the slope to create a line segment. Okay, so to do that, you're going to take the slope and you're going to take the point, right? If we've got a slope and we've got a point, we can combine them to find the line that goes through that point with that slope using point slope form. So it's just y minus y naught equals f of t naught comma y naught times t minus t naught. All right, so that's the line equation. Okay. And then next we can go through and move the y naught to the other side. And so we get y equals f of t naught comma y naught times t minus t naught plus y naught. All right, so what this is the equation of a line that goes through our starting point with the slope that we want. Okay, and now you can plug in t values and out will come y values. All right, so if you plug in a t value, out will come a y value. And what we want to do is we want to plug in the t value where the next the next slope calculation we want to do is. Okay, so what you can do is you can just take, so we're going to say y1 equals f of t naught comma y naught times t1 minus t naught plus y naught. Okay, and so this enables us, the result of that, all right, is going to give us, we're going to end up with the point t1 comma y1. So we started with t naught y naught, we did a bunch of stuff, and then we stopped, our result was t1 y1. Let's jump back over to the picture just to make sure that all of this is that you can see how all of this fits in with what we've been doing. All right, let's zoom in even a little bit more. Oh, that's really zoomed in. Okay. All right, so what we've been doing, so we'd say this point here, this would be t naught comma y naught. That's our starting point for this curve. All right, and what we did is we took the slope there, that flat slope. All right, we went through and we found that. So we found f of t naught comma y naught. Okay, that gave us the flat slope that's right there that you can kind of see the back half of. We then used that slope to define a line that went through that point. That's this line segment right here. Okay, so that line segment, technically, if you just had the equation of that line, it goes all the way across the picture from one side to the other. And then what we did is we took that line, that entire line, and we stopped it here because we want to do a new calculation here. So this point here would be T1. Okay, so we went through and took T1, plugged it in, and what does it produce? It produces Y1, which is going to be the height of that point. So when you take T1, plug it into the line equation, you'll end up getting Y1. And in this case, because the slope is 0, T1 is good. It looks like T1's 1/2 with the way that we did it. So T1's 1/2, and it looks like Y1 would be 0. Right, so the result is going to be that we're going to end up with a point T1 comma Y1 there, and that point in this case, it looks like T1 is going to be 1/2 and Y1 would be 0. All right, and then I'm going to jump back over in a second and find the next point. But the way that what we're going to do from here is we just do the exact same thing over again. So what we're going to do is we're going to take T1 Y1, we're going to plug it into our direction field, right into our differential equation to find the slope that's right here. We're going to take that slope and we're going to combine it with we're going to use the point slope form to define the equation of this line. And then once we have this line, we're then going to plug in T2, which would be right here. We're going to plug in T2, and what it's going to do is it's going to produce Y2, which is going to be the Y coordinate for this point. And then the net result is that we'll have T2 comma Y2. And you can just march along, starting with T naught Y naught, then T1 Y1, then T2 Y2. Each time you find the slope, you find the line equation, and then you plug in the next T value. So that's how it works. So, okay, hopefully that is clear. So let's jump back over and I can show you that. All right, so we started with T naught Y naught. We did a bunch of stuff. We got to T1 Y1. All right, so what happens next? Next, we just do the whole thing over again. You're going to find the slope first by taking T1 Y1 and plugging it in. All right, that's the slope. Next, you're going to find the line segment, or the line equation by plugging, T1 Y1 into point slope form. So we get Y minus Y1 equals F of T1 comma Y1 times T minus T1. Then you can move Y1 over. We get F of T1 comma Y1 times T minus T1 plus Y1. And now at this point, this is a line equation. Or it's a line function actually, and you could go through and plug in T values and out will come points that are on that line. And the specific T value that we want to plug in is the next increment. And so to get the next increment, we want to go to T2. And so we're going to plug in T2 and you'll get Y2 equals F of T1 comma Y1 times T2 minus T1 plus Y1. And the result of this is going to be the point T2 comma Y2. And you can just continue this, and each time you'll end up getting the next point. And so putting this together, just seeing the pattern here, right? There's a pattern. You slope, line equation, move the Y over, plug in, next point, and so on. So if putting it all together, right, what does the result end up looking like? Well, it ends up looking like, just if we combined all this stuff, it ends up looking like Y of n plus 1 equals F of Tn comma Yn times T of n plus 1 minus T of n plus Y of n. All right, let's just kind of compare, right? So the two lines that this matches with are here and here. They're the final lines that we ended up with, right? So you have y sub 1 goes along with t naught and y naught. So that's why it's n plus 1 and n and n. And then you've got t sub 1 minus t sub naught, t sub n plus 1 minus t sub n plus y naught, right? So if you took the equation we just came up with and you plugged in n equals 0, it would produce this, right? And what about this guy? Yeah, does this guy work as well, right? So we've got 2 goes with 1 and 1, right? So if you plugged 1 into this, you'd get a 2 here, and then a 1 and 1, and then 2 and 1, 2 and 1, and 1. Yep, that does work. All right, so if you were to go through and continually increment, this could be a formula that we could use that would go through and generate outcomes, for each case. Okay. So that's the next thing that we want to do, is to actually go through and try this. Oh, hold on. I forgot one thing here. So this t sub n plus 1 minus t sub n, this is the same every time. Okay. If you look at the example that we just did, right, it was 0.5, right? So we went 0 to 0.5, then 0.5 to 1, then 1 to 1.5, if you go back and look at that picture. And so this is typically called the step size, because it's the size of the steps you take before you recalculate with a new slope. And so what we're going to do is we're going to replace it with h, since it's the same every time. And so our final formula for going through and applying Euler's method is going to be this formula. Okay. And so that's where the Euler's that's where the method comes from. Oh, I'm like blanking about it. I don't think I've explained this. The name of this technique is Euler's method. So I may have littered that throughout the video without making that explicit. So this technique, this numerical technique, was came up with by Euler, and so that's why it's called Euler's method. Euler's a famous mathematician. Very interesting person, has a lot of theorems and techniques named after him. I highly recommend a quick Google search to learn more about Euler. All right, let's go through and actually apply this technique to solve a differential equation, numerically. Okay, so we need to start off with a differential equation, first order differential equation. We've got 3 minus 2y, or sorry, that's supposed to be a t. 3 minus 2t minus 1/2 y. And we have an initial condition, y of 0 equals 1. And we're told to use a step size, h, of 0.2, right? So last time we did 0.5. This time we have a smaller step size, 0.2. So we're going to do new calculations every 0.2 for t. All right, so the way that you can go through and set these problems up is you can set them up in a table. And so that's the way that that I'm going to do it. Or if you're very enterprising, you could go through and set them up in an Excel spreadsheet, which I have done before. All right, so let's just say we'll start off. We're going to have a table. It needs to be a pretty big table. Hopefully that's big enough. Okay, so we're going to have entries here. All right, so hopefully that's big enough. And then, so here, this is going to represent n. So we're going to have a column for n that will show where we are in our increments. T sub n, y sub n. We're going to have a column for finding the slope. T of y sub, yeah, I can already see this is probably not going to work. Let's see, is it going to fit? All right, so we're going to get 3 minus 2 t sub n minus 1/2 y sub n. Oh, barely. All right, and then this column is where we're going to go through and put our formula that we had from the previous page. So y sub n plus 1 equals f of t sub n comma y sub n times h, which is 0.2 in this case, plus y sub n. All right, and that looks good. All right, and so the way that this works is you start off, you've got n equals 0. N equals 0, we're going to start off with our initial values. So when n is 0, we're going to have t naught, y naught. All right, so t naught is 0, y naught is 1. We're going to use that t naught and y naught. We're going to take those, plug them into the slope to figure out what the slope would be. And so I've already done the calculation, so we're just going to pop it in here. So it's 2.5. And then once you've got the slope, you're then going to take the slope and t and y, t sub n and y sub n, and plug them into this, right? And so one important thing about an incremental technique like this is that you need to be able to define the next value, y sub n plus 1, using only previous values, right? So you can see how we only have t sub n, y sub n, and y sub n. There's no n plus 1s on this side. So you need to be able to define the next value using previous values. And so we can do that, right? Because we have t sub n, y sub n, f of t sub n, y sub n. Just take those three things and plug them into this. And you can check this with a calculator. You should get 1.5. All right, so what does that mean as far as doing the problem here? What does that mean? Well, it means that for n is 1, the next point, we know what the next t value is going to be. We know what t sub 1 is going to be because we're incrementing t by the step size. So if we start off at 0, the next step is going to be 0.2. And then what's y sub 1 going to be? Well, it's the outcome that we just calculated, 1.5. Okay, and so that's the completion really of one increment. It looks like that. All right, you start off with a value, find the slope, create the line segment, and then figure out what the output would be, for when if you plugged in 0.2. And then take that outcome, start over, plug it back in here, and then we have the next point. So the next point is at 0.2, 1.5. We then can use those two to find the slope there. So it's going to be 1.85. And then if you take the slope and then t sub 1, y sub 1, plug them into this equation, and out comes 1.87. All right, and so we have, when for n is 2, we're going to have 0.4. How do I know 0.4? Well, just add the step size again. And then what's y going to be? This is the y sub 2. It's going to be the previous, the result from this column. And so we're going to have 1.87. And then to find the next value, you take those two, plug them into the slope first. Out comes 1.265. Then take those three things, plug them into this equation here, and you generate 2.123. And then what is that? What does that mean? So that means that for t sub 3, y sub 3, we'd have 0.6, and then that result 2.123. Okay, and so if you only wanted to go through and figure out what the outcome to the differential equation would be at where t is 0.6, you could just stop there, right? So you only need to go as far as where you want to figure out what the value would be that would work for the differential equation. But I mean, if you want to go all the way to 1, you can just keep going. So if you plug these two into our slope formula, you get 0.7385. And that corresponds to 2.2707. All right, which means that when n is 4, where we'd have 0.8 for t, then y sub 4 is going to be 2.2707. Then if you want to figure out the next one, take those, plug them in, you get 0.26465. And then that produces 2.32363. And so when n is 5, we get 1 for t, and we get 2.32363. And then we're going to stop there. All right. And so what is this? So again, what does that tell you? That tells you that the point that's going to work for the differential equation with initial condition 0, 1 is going to be 2.32363. Okay, and so that's an actual solution to the differential equation itself. And we were able to go through and find it without doing any solving at all, just by going through and taking slopes and line segments. Okay, so you might be skeptical. That would be perfectly rational. You might be skeptical. Does this actually work? Well, the differential equation that we chose is one that you could go through and solve, right? It's a linear first order differential equation, so we could go through and solve it. What happens if we solve this? Let's go through and solve. Well, we're not going to solve it actually, but I'll write the solution. So given these values here, the solution to the differential equation would be y equals 14 minus 4t minus 13 e to the negative 1/2 t. So that's the solution using this information here, and just solving it using, you can use integrating factors to solve it if you want. Okay, so how does it work, right? So this solution, well, the whole point in solving the differential equation is not just the function that you get, but the actual points that would correspond to it. And so we can plug points into this and watch what happens, right? So what is y of 0? Y of 0 is 1. What is y of 0.2? Y of 0.2 is 1.43711. What is y of 0.4? We would get 1.75650. What is y of 0.6? We would get 1.96936. And let's just do the last two so that we can compare them. 0.8, we get 2.08584. And y of 1, which would equal 2.11510. All right, so this is an actual function that you could plug into the differential equation that makes it true, and these are the corresponding points, right? A function is made up of points if you plug them in, and so we can compare the points that you'd get if you actually solved it using symbolic manipulation to the points that we got by solving it using the slopes and line segments. Okay, and how do you compare these two? Well, the things you want to compare, these are the y values that correspond to t values. So you can see that when y is 0, t is 1. Y is 0, sorry, when t is 0, y is 1. T is 0, y is 1. And so the initial conditions, of course, perfectly match up. So for the next point, when t is 0.2, our slope and line segment method produced 1.5. The actual should have been 1.437. So, you know, we're off. It's not perfect. It's an approximation. That's why it's called a numerical approximation method. For 0.4, we've got 1.87. The actual 0.4, 1.75. And then 0.6, 2.123, 0.6, 1.969, and so on. Okay, so that's the result of our numerical technique using Euler's method, and that's our actual results. So let's compare the two. Let's actually look at a graph and compare the two. All right, so here we have a graph using Geogebra. If you go to Geogebra and type in Euler's method, you should be able to get a tool that that looks like this, where you can plug your differential equation in, you can plug in your initial condition in, you can plug in your step size, and it will show you the actual solution, assuming it's solvable, and it will show you the result of Euler's method for that step size. All right, and so we could see visually how the two solutions look. All right, so this is actual, is the purple, and our approximation is the blue. So good, bad, open to interpretation. You know, you can go through and you can make your own qualifying decision. However, if you don't think it's good, what we can do is we can always change the step size, right? That is not fixed. There was nothing that said that we had to do 0.2, right? What if we went through and made the step size a little smaller? What happens? Whoa, the approximation becomes more accurate. What if you made it smaller yet? Oh, it's fitting. It's almost fitting right on the actual solution. I don't know the limit of how far you could go with this. What happens if we got really tiny? It's almost right on top of it. You know, you could go through and you can make this as tiny as your your calculating potential, right? So whatever system you have, I don't know if it will do 0.01. No, there is a limit, right? But you could go as small an increment as you can go through and calculate, as small as a computer that you have the potential to be able to go through and work with, you know, to find approximations to as many decimal places as are necessary for the problem that you're solving. Okay, so that's a really neat, wonderful result. And that is that when we encounter a differential equation that we can't solve by hand, we can go through and we can get solutions that are as accurate as we want by just going through and using this numerical technique, which is incredibly simple. It's just a slope and a line segment. Okay, so what are the problems with Euler's method? Does Euler's method always work? Is it perfect? Like, why do we even bother solving differential equations with symbolic manipulation if we can just use Euler's method? Well, so there are problems with Euler's method. It's not perfect. So, you know, when does this numerical technique not work? Let's just talk about that for a minute. So the thing that you need to think about if you're going to analyze when Euler's method works is the technique that we used. So we went through and we used a slope to calculate a line segment, and then we used that line segment to pick the next point. All right, so since it's based upon the slopes from the direction field, if you get a large change in slope over a small distance on the direction field, then that's a problem for Euler's method. Okay, so that's just something to note. Since Euler's method is based on slopes in the direction field, Euler's method does not work when you get a large change in slope over a small distance in the field. All right, so what's going to happen then is you're going to the actual solution is going to move much more quickly. There's going to be a delay. The actual solution is going to move much more quickly than your approximation is going to. And you can try and counteract that by going through and dialing up the step size, okay, but that's going to still be an issue. It's just going to reduce the effect, so it's still a problem. All right, so when do you have what can we look for to try and tell when we're going to have this situation where there's going to be a lag with the numerical technique versus the actual solution, where we're going to see a large change in slope over that small distance, so that the incremental technique is going to have that delay. It's going to have that problem. All right, so this occurs when the solutions of the differential equation are far apart. And what I mean by that is, I mean that if you went through and were to graph solutions for initial conditions, you see those solutions diverging, they're spreading apart, okay, in the picture. All right, we actually can talk about when that happens. This is an interesting thing. If the differential equation can be solved, we can see what would cause this. All right, so if the differential equation can be solved, the way that we can see this, right, in the result is by looking at the C term, the term that contains the C that we went through and came up with when we solved the differential equation. So to give you an example, right, well, if we go through and take the differential equation that we solved earlier, if rather than solve it with the initial conditions like we did, if we had just had not used the initial conditions, right, you end up with the general solution of the differential equation looks like this. Right, so this is the general solution of the differential equation from earlier, so where we haven't solved for C. Now, if you take a look at that C term, what happens as T gets larger, right? So think about the fact that if we go through and graph a solution of the differential equation, as we go from left to right across the graph, T is going to be getting larger. And so looking at what happens as T increases will tell us something about how far apart the solutions are, because the C here is what separates solutions. Okay, so let's just slow down here and think about that for a moment. You go through and you solve a differential equation and it produces a C. So if you have 0, 0 as your starting point, as your initial condition to your differential equation, you take that initial condition and you plug it in and it gets you a C value. Right? Let's say you go through and you have 0, 1 as your initial condition. You plug that in, that gets you a C value. Right? So though the difference apart, right, initially is going to be 1 unit, because one is 0, 0 and the other one is 0, 1. And the question is, what happens over time? Do they stay 1 unit apart? Do they get closer together, right? One of the things that you can look for to determine how they behave over time in terms of their distance apart, right, how far apart the solutions are, is what happens to that C value. Okay, and because of this exponential piece that's attached, what can we say about the C value as T gets bigger? right? So because of that negative exponent, that t value is, as t gets bigger, that's going to cause that exponential term to get smaller and go to 0. And so that's going to cause the c term to go to 0 as we move across the graph from left to right. And so the solutions are going to get closer together. They're going to approach the same value. All right, so the way that we can interpret this is as t goes to infinity, the c term is going to go to 0. Right? So thus, the solutions approach each other. So the distance between solutions gets smaller. Okay, so what that means as far as Euler's method is concerned is that this is a good example. This is going to be a good case, I should say, a good case for Euler's method. Euler's method is going to work great on a problem where the c term ends up going to 0. Let's just spend a minute, though, and show a case where Euler's method doesn't work so great. What if we tried Euler's method on the following differential equation, right? So if we have dy dt equals 4 minus t plus 2y, and we have y of 0 equals 1, and we have h equals 0.1. All right, what happens? I'll just show the actual solution in the table, and then we can talk about what happened, all right, what the issues are. So let's say we have t equals 0, t equals 1, t equals 2, t equals 3, t equals 4. I don't know why I'm writing all these because I just put just t at the top. T equals 5. All right, and then if you actually solve the differential equation, this is the exact solutions. And then if you use Euler's method, this is the approximation that you get. So the exact solution. So we're starting at 1, t equals 0. We're starting with y is 1. And then at t equals 1, the exact solution would be 19.0699. Euler's method produces 15.777 okay, and so this, you can see Euler's method is already lagging behind the exact by 3 and a change units. All right, so at t equals 2, the exact solution is 149.3949. Euler's method gives 104.6784. And let's just fill in the rest of these and then we can comment on them. So we get 1109.179, then 8,197.884, then 60,573.53. And for Euler's method, we get 652.5349. We get 44,042.122, and we get 25,026.95. And so error-wise, you can see we start off with we even start off with a fair amount of error, even by t equals 1. I mean, this is like what almost 4 units, well, 3 and change units on 15. So what's that, like 20%? So we're already at like 20% error, then 50%, close to 50% error by t equals 2. We're already approaching 100%. Well, we had 100% error here at t equals 4, and and then even higher, right, at t equals 5. Okay. And so Euler's method did not do a good job here with 0.1, which increment wise, we used 0.2, which is double that, with the previous example, and it worked okay. You can see, so this produced a ton of error with 0.1. If you actually go through and solve this differential equation by hand, again, you can use, this is a linear first order differential equation, so you can use integrating factors to solve this. You'll get y equals -7/4 plus 1/2 t plus c e to the 2t. All right, so look at the c term here. What happens with the c term? As t goes to infinity, right, as t gets bigger, it doesn't have to go to infinity, you just have to go to 5. As t gets bigger, what happens, right? The c term explodes in value because it has this positive exponent. So the c term goes to infinity. So the solutions, right, the solutions of the differential equation. So here we start off with 0, 1. You could have started off with 0, 0 or 0, 2. They are spreading further and further apart, right? The solutions are spreading apart as t gets bigger. And that causes Euler's method to struggle, right? It falls behind. One way to think about it actually is that at this point, Euler's method is going through and it's now on a different solution curve, right? The actual solution curve has, where t is 1, you have 19 as the point. We're now on the solution curve where t is 1 and 15 is the point. And so that's a different curve. And since the curves are spreading apart, you just kind of fall behind and lose track of the actual solution, and you can't get caught back up. Okay, and so that's the basic idea behind Euler's method. Oh, and one other thing I almost forgot to mention that I did want to mention. So to be clear about talking about all of this, when does it work? What are the circumstances? To be clear, you're not going to be applying Euler's method to differential equations that you can actually solve. You're only going to be applying these numerical techniques when you can't solve a differential equation. If you can solve one by hand, right, then you don't need this numerical technique. You just go through and solve it, and then you've got all of the solutions at your fingertips just by plugging in an input. So you're not going to be able to solve the differential equation to figure out whether this is the case. So instead, the way that you can look at it, right, is that if you go through and use Euler's method and it works, right, it works well, then it implies that the solution of the differential equation, right, implies that the distance between the solutions went to 0. How would you be able to tell whether it's working well or not? Well, what you could do is you could go through and you could apply different, you could go through and you could have some calibration, right? So if you're working with a tool of some kind in a setting, I don't know, designing a bridge, whatever, you'd go through and you do some calibration to know what solutions you expect to be in the neighborhood. So that would tell you if your solution from Euler's method is wildly off, right, from your numerical technique. It would tell if you're wildly off. So that's what calibration is for, is to go through and say, all right, well, that we expect a solution in this neighborhood. If we end up getting something that's wildly different, then clearly it didn't work. And so this must be a circumstance where we have this happen, where we have the solutions are spreading apart and blowing up. So the whole point of this last segment of the lecture is to just talk about what's happening. You won't know if that's happening or not. This is just an explanation for why it didn't work. Okay, anyway, so that's now clear. Thank you for watching, and I hope to see you next time.